what have we done? What do we still need to do? So I don't really want to cover any new material today. On Monday, we're going to talk about Cauchy sequences in detail. But you should have enough to do the homework that's due on Wednesday. That really is going to go over this idea of dense sets, which I think you can just kind of read from the problem set itself. And then the next problem set 5 that's due Friday, that really is going to go over Cauchy sequences in some detail. But we'll talk about Cauchy sequences on Monday. I thought for today, though, that we can kind of take a slight break and just go over the problem sets, just things that we haven't done, and maybe talk about in more detail the ones we've already gone over. So I think that all of the slides should be there in Sakai. If you can't find them, please let me know. But I am going to go over those and try to go over those somewhat slowly. Just as a caveat, those slides are pretty detailed. So they have everything. So we're not going to go over everything in the slides today, but just saying that if there's anything that we don't go over or anything that you're unsure about, they're all going to be right there in the slides. Okay. All right, so let's maybe get started here. So I'll start by sharing my screen. And let me move things around so I can see all of you. Okay. So I'll just start off with a few quick announcements, and then we'll try our best to recap what we did on Wednesday, and then I'll try to go over some information about the problem sets that we've done so far. Right, so just as a reminder, the last lecture is on YouTube, so if you have any trouble with it, just please let me know, but hopefully everything is right there. We are going to have office hours, usual time, usual place, so it'll be 11 to 12 after this lesson, and then 4 to 5 in the afternoon today. So I'll be around for both of those. As a reminder, there actually is a whiteboard feature here in the system, so I can easily go in and kind of make comments and draw things on the whiteboard. So we can certainly do a lot of math there in Zoom. We do have mentor sessions. They are Sundays, Mondays, Tuesdays, and Thursdays from 6 to 8. So just feel free to kind of join in over Zoom. You can kind of hang out for a few hours to see what's going on. And then finally, for the problem sets, as I mentioned earlier, problem set 10 will be due Wednesday. Sorry, homework assignment 10 will be due Wednesday, and problem set 5 will be due a week from today. By due, what I mean is we're going to try to go over them over Zoom. I'm not totally sure how this is going to work, but please try your best to have solutions ready to go on Friday, April 10th. And we'll just try it out, see how it all works out. Homework set 9 is due today. So I think that most of you, if not all of you, have already uploaded it into Sakai. If you haven't, or if you're having any trouble, just let me know, but it'll be due by 5 p.m. today. That way I can hand it off to the graders and hopefully they can grade them over the weekend. All right, so any questions before we get started here?
The homework is to be uploaded on Dropbox, right?
That's correct. That is right. And if you have any trouble, just send it to me by email, and then I can put it into Dropbox for you. All right. So let's do a quick recap of what we did on Wednesday. Now remember, we're working with a complete ordered field. So you can say here, think of F as like the real numbers. And let's pick a number that's greater than or equal to 1. All right, so this could be like the number 2 if you want. So first, we defined a sequence in this way, and I'm going to come back and talk about the sequence in more detail today. But we have the sequence where we're going to write the next term in the sequence as pt plus p divided by t plus p. And the sequence satisfied a couple of really nice properties. Number 1, it's an increasing sequence, but t squared is less than or equal to p. Right, so it's going to start at 1, it'll increase. So this sequence is actually bounded. It's bounded below and it's bounded above. Right, it's not less than 0 and it's not greater than p. Number 2, if maybe tn squared is very close to p, so what that means is if I add epsilon to it, then it'll be greater than p. Right, so again, if tn squared is very close to p, if I add just a little bit, it'll be a little bit greater than p. Then the next term in the sequence is even closer to p. Right, so again, if tn squared is close to p, then the next term in the sequence is even closer to p. That's what this says. So if you don't feel comfortable with kind of this fancy math language, we can just say it here in words. We have a monotone increasing sequence such that t squared is less than p, and t squared is as close to p as we want it to be. Right, that's what those first two statements mean. I have a monotone increasing sequence, tn squared is less than or equal to p, and tn squared is as close to p as we want it to be. So we also defined a similar sequence. So in this case, we'll define the bn's in this way here. Right, so bn plus 1 is 1/2 bn plus p over n. And this also had two really nice properties. So first, we have now a decreasing sequence. So this sequence is also bounded. So it's bounded above by p and bounded below by 0. So same thing as before. But now, bn squared is greater than or equal to p. So it's a slightly different inequality from before. And just like before, bn squared is going to be greater than p, but if I maybe subtract epsilon so that now I'm slightly less than p, then the next term in the sequence is even closer. Right, so again, that's what that says, that if bn squared is very close to p, then the next term in the sequence is even closer to p. So here's another way to say this in different words. We have a monotone decreasing sequence. So bn squared is greater than or equal to p, and bn squared is as close to p as we want it to be. So I wanted to put all of this out there for you just to say that there are different ways in which you can take square roots. So you can get as close to the square root as you want. I mostly am going to use the very first one here for an example that I want to go over today, because I want to use this concept of if tn squared is close to p, then the next term in the sequence is even closer to p. Okay, so any questions so far, just on the recap here? Right. Okay, let's move on a little bit. So as I said before, the idea today is just to review all of the problem sets that we've done to date. So I want to make sure that we'll actually go over the problems to see if anyone has any questions about maybe what we did in class, what we didn't completely go over. So let me start with just an overview of what will happen with all of the problem sets. So in general, we're going to have 6 problem sets, and you can see the dates here. We've done 4 of them, and we have 2 left. So problem set 5 will be due next week, and then problem set 6 will be due pretty much in a couple of weeks. So far we've done problem sets 1 through 4. And here you can see how many problems are on each set. So remember that these will all be due by the end of the semester. The seniors will have to turn this in a little bit earlier. I recommend that once you're done with the problem sets, try to turn them in so that way I can grade them and you can get feedback on how they're all being done. So say if you've already completed problem set number 1, go ahead and turn it in. I'll grade the problems for you, and then you can keep working on the rest of the problem sets. Yeah, Lawrence, did you have a question?
Yeah, I think I received an email saying that senior grades are now due May 21st because commencement was postponed. So would we still need to be turning that in early, or are we okay?
I would say probably not, because everything's going to be due May 15th anyway. It'll be better for me if you turn them in earlier, then that way I can kind of grade them and get more feedback to you. But yeah, but if you needed more time to turn them in, that'll be fine as well. Okay, all right. Any other questions here about the due dates or the problem sets?
Yeah, if we don't tech them up, how do you want us to turn them in if they're just handwritten?
just scan them in, hand them in. So just like with the other homeworks, you can scan them in, upload
Mhm.
everything to Dropbox.
Okay, thank you.
Yeah, you're welcome. Okay, any other questions? All right. Okay, as a reminder, when I say due dates here, what I really mean is these are the dates we're going to present them. Right, so not the dates you have to turn them in, but these will be the dates that we'll present them. So by due dates, I mean, I'm hoping that you'll work on them, you'll get a pretty good idea of how to do all of them, and then you'll be prepared to present them here during the class period. So I want to go through the first 4 problem sets in detail. So I want to go through each of the problems here, all, what is this here? 21 of them in detail, just say 25. So here's problem set number 1. There were 6 problems. We actually did 4 of them in class, and then there'll be 2 of them that you should complete on your own. So I'm not going to go over these here in detail. Let me just kind of quickly go through them one by one to remind you what we did. But I do want to go over the 6 problems here. So the very first problem said, show that n is a multiple of 3 if and only if n squared is a multiple of 3. Right, so here I've just copied the solution that I had in the lecture notes, and this was almost exactly what was covered in class. Right, so if you wanted to use this as your own solution, feel free to, because we did cover it in class, so it's fair game. If you want to come up with your own solution, that is perfectly fine as well. Right, so whichever you'd like to do will be perfectly fine. Right, and as a reminder, we basically did this in the lecture notes back in lesson 4, where the number 3 was really replaced by the number 2. Okay. So again, I'm not really going to go over this here in detail because we've already done this in class. And I just wanted to show you here on these slides that if you didn't really have this in your notes somewhere, everything is still here. Okay. Any questions here about the first problem? Okay, all right, let's move on here. Similarly, the second problem we did in class, so it was to show that the square root of 3 is irrational. So I'm just showing here on the screen how the proof went. This here is basically the proof that was given in class, so I just had everything here on the notes. Again, you can use what's here, you can copy it word for word because it was in class, so it's fair game. If you want to come up with your own proof, that is perfectly fine as well, whichever one you feel more comfortable with. And again, this here is also in the lecture notes, lesson number 4, where 3 was replaced with 2. So any questions here on problem 2? Right, let's keep going then. Problem 3 was one of the long ones here that dealt with things like the cancellation laws, showing that the additive multiplicative identities were unique, the additive multiplicative inverses, or at least the additive inverses were unique. So this here, I do want you to complete on your own. We did not quite do this in class, but we did several of these in class. So if you actually look at the lecture notes from lesson number 8, there were a lot of these 6 here where we did them. So for example, we did do in class that 0 is unique, that 1 is unique, negative x is unique, x inverse is unique. So certainly you can feel free to look at the lecture notes and you can copy the proofs there, again, because it was in class, it was fair game, so it's perfectly fine. If you want to come up with your own proofs, that's perfectly fine as well. Okay. So any questions here on problem 3? All right, let's keep moving. Problem 4. So here, if A times B is 0, then either A is 0 or B is 0. We also basically did this in class. So I just showed here the proofs. Of course, you know, remember that we did this by going over the various axioms and using some of the properties. This was also basically done in the lecture notes. But again, I have the proof here because it was simply done in class. Okay, so any questions here? All right, let's move on. We have 2 more to go. Problem 5 was supposed to show that if you have the sum of 2 rational numbers is rational and the product of 2 rational numbers is rational. We didn't quite do this in class, but I know with several of you, I did this during office hours. So I just have a sketch of the proof here. The idea is that you just say let Q and R be the ratio of two integers, then the sum is the ratio of two integers, the product is the ratio of two integers. So there's really not a whole lot to show here. It's just a matter of being careful with the definitions. So again, problem 5 really was saying look at the definitions. You can take it for granted that the integers are closed under addition and multiplication. You don't have to prove those because we're just taking those for granted here in this class. So again, we didn't quite do problem 5 in class, but I know that I did this for several of you during office hours. Okay, so any questions on this one?
Yeah, to clarify on that, we would have to prove all of the field axioms given those definitions for this proof to be sufficient.
I would say no. I would say that really the whole thing of this one is just noting or really asking the question, what's the definition? So that's what I'm saying, that the proof that's here is really the only proof that you need. Right? So you just have to ask yourself, what's the definition of the sum of two rational numbers? What's the definition of the product of two rational numbers? Right? I would say that most of the rest of them about like, the additive identity and the inverses, most of those don't really worry about because it's not worth it for this problem here. Okay, other questions? Okay, let's move on here. So problem 6 is another very long one. So there were 10 parts here. This also I want you to do on your own. And this here, there are several parts where these were in the lecture notes. So for example, the statement that 1 is greater than 0, or the statement that x squared is non-negative. Those we actually did in class, and those are in the lecture notes. The rest of these you definitely will have to work through and do on your own. That's why I was saying for problem 5, I'm not so interested in the different field axioms, but here for problem 6, there are 10 parts. I definitely want you to work through all 10 parts here. Okay, so any questions here on problem 6? Any questions more generally on problem set 1? All right, so let's move on then to problem set 2. So there were 5 problems, and fortunately we did almost all of them in class. So I want to go over the 5 that we had here. So the very first one had some statements about the absolute value. And these here, I definitely want you to do on your own, but luckily many of these statements we did in lesson 10. So these actually were in the lecture notes. So not all 6 of these, but I believe maybe 3 or 4 of these are in the lecture notes. So I would definitely say to take a look at the lecture notes to see how this works out here. Okay, so let's go on to problem number 2. So here this says x is less than y if and only if x squared is less than y squared. So we kind of did this in class, but here I just have a sketch of how the solution goes. So again, what's here is certainly going to be fair game because we basically did this in class. So I would just say you can feel free to use this in your own write-up or do your own proof. Either way is perfectly fine. Okay, so any questions here on how we did problem 2? Okay, so let's move on. Problem 3 was the triangle inequality. Now, this here actually is in the lecture notes. We didn't really do this in class. I think that we did maybe 1 or 2 parts because it's kind of a long, nasty proof. But here in the lecture notes, I've just copied what was in the lecture notes here for this slide. You can see that it's basically 5 cases that you have to kind of work through. So again, you can feel perfectly comfortable to copy what's here in your own write-up, or you can come up with your own write-up. Right? Part of the reason I'm putting it here is just to say we did it in class, so it's here, it's already in the lecture notes. So you can feel free to do this however you like. Okay, so any questions on this problem? Okay, all right, let's move on here. So problem number 4, this is another one that we did in class. So show that the absolute value of a is less than epsilon for every epsilon if and only if a is equal to 0. So here I just have just a write-up of what was in the lecture notes. So you can take a look at where this was written up in lesson 10, right? But again, we basically did this one in class as well. Okay, any questions here on problem 4? Okay, here's the last one for problem set 2. So we want A less than or equal to B plus epsilon for every epsilon, if and only if A is less than or equal to B. So here I have a sketch on how the proof goes, and we also basically did this in class. So essentially the proof here is something like proof by contradiction, right? So if we assume that A is not less than or equal to B, then A is greater than B, and then you just cleverly choose an epsilon and things work. So mainly I wanted to emphasize here that this type of proof we can use over and over and over again. So it's not so crucial that A be less than or equal to B plus epsilon. You can really say let A be less than B plus epsilon, and the same type of proof is going to work. Right. But again, we basically did this proof here in class. Okay, so any questions here on problem 5? Okay, so let's move on to problem set number 3. And here there were a few that we did in class, but maybe we didn't do it all the way through. So here's where I do want to spend some time today and actually try to go over some of the proofs that we didn't do all the way through, just to make sure that there's no lingering questions about how some of these are to be done. So there were 9 problems that were to be done on problem set number 3. All right, so the first one was to show that the infimum and the supremum exist and they are unique. So I'll say that that one I'll let you do on your own, but here's a hint on basically how to do it. So let's say that there maybe were 2 least upper bounds, and let's call them S1 and S2. Well, by the trichotomy law, either S1 is equal to S2, S1 is less than S2, or S1 is greater than S2. So of course, we really want to prove that the 2 least upper bounds are equal, that S1 equals S2. Well, if they're not equal, then say S1 is less than S2, right? So that would be this one here. Well, the problem is that S2 is the least upper bound, so S2 has to be less than or equal to S1. And of course, that's the contradiction. Right, so the same thing happens if you're dealing with the infimum, right? Same concept. But again, I just wanted to kind of sketch out the hint for those of you that might be wondering about this one. So any questions here on problem 1? Okay. All right, let's move on here. All right, so problem 2 wanted us to look at how the infimum is related to the supremum of the negative of a set. So again, I want you to do this on your own, but the whole point here is that you just realize that, say, if B is bounded from below, then you can just kind of switch around the inequalities here to say that negative B is bounded from above, right? And then hopefully the rest of the proof is not going to be too hard. But if you do have any questions about this, I'm more than happy to answer them during office hours. Any questions, comments on problems number 2? Okay, let's move on then to problem 3. So this one we did do in class. This was the one about the supremum of A plus B is less than or equal to the supremum of A plus the supremum of B. I'm not going to go over the proof here, but I'm going to say that the exact proof that was given in class is just written up here in the notes. So this was done in class on Wednesday, February 26th. So you can just kind of look at your notes there if you have any questions about this problem. Okay, so any questions on problem number 3? Okay, all right, let's move on to problem number 4. So similarly, this was also done in class. So this just says that if A is contained in B, then the supremum of A is less than or equal to the supremum of B. And again, I've just written up the proof here. This is just what was done in class. So this was also done on Wednesday, February 26th. So any questions or comments on problem 4? Right. Problem 5, we also did in class. So this is the whole thing of that you have this set A plus C, or the set C times A. So now you want to say something about the supremums here. So I believe that in class, we went over parts 1 and 2. Right, so here I just have the basic setup for part 1, and then here's the basic setup for part 2. I'm not going to review this because we basically did this exactly in class. I just wanted to say that here's kind of a sketch on how to do this for part 3 that comes down to using problem 2 on this problem set. Right, so I know that we just kind of said this very quickly in class that there is a way to do this, but this here is just saying that if you want any hint on how to do it, then here's an idea. Okay, so any questions here on problem number 4? Right. Okay, problem number 5. So maybe I'll say a few words about this because I think that we went over this, but there might have been some confusion about it. So this says, show that S is the supremum if and only if we have these two inequalities here. So for the first one, you can say, let's first assume that S is the supremum. Then of course, if S is an upper bound, then we'll have this inequality here rather easily. Right, so X is less than or equal to S, but S is less than S plus epsilon. So the first inequality is actually not that bad. For the second inequality, of course, we want to show that there exists some X such that S plus epsilon is less than X, but you just do a proof by contradiction. So you assume maybe this doesn't work. And then what you find is that there's actually another upper bound, namely S plus epsilon has to be an upper bound, and you run into a contradiction. Right. Going in the opposite direction, I want to emphasize this because we've only kind of skimmed over this a little bit. Let's assume that statements 1 and 2 are true. Right, so that is for every epsilon, we have the statement about S plus epsilon and S minus epsilon. What I want to prove is that that S is the supremum. So, first of all, from the first statement, right, from 1, if X is less than S plus epsilon, then the supremum of A is less than or equal to S plus epsilon. But we just worked out on the last problem set that if this is true for every epsilon, then the supremum has to be less than or equal to S. Right? Now, if we use the second part, then we'll find that S plus epsilon is less than the supremum. So we can just kind of add epsilon to both sides to find that S is less than the supremum plus epsilon. And by the same problem from problem set number 2, now we get the other direction, right? That S is less than or equal to the supremum. And so that gives equality. So I know that we actually did go over this proof in class, but I just wanted to make sure that everyone is okay about this because I have gotten a couple of questions about what happened here. So this is 1 and 2 imply S equals the supremum. Okay. All right, so any questions here? All right, let's keep moving then. So problem 7 said to prove an analogous result from problem 6, but now for infimums. So I do want you to show this on your own, but as a hint, this is really what you should show. Right, so if you're kind of stuck on maybe how to do this, then the inequalities do get moved around, but kind of the idea is that you first, if you start with B, you construct this set A, which looks like negative B. So just here in the slides, I've written down the statement that you should attempt to prove if you're stuck on how to do this one here. So any questions here on problem 7? Right, so let's keep moving. Right, problem 8 says if u is an upper bound and u is an a, then u is equal to the supremum. I'll just skim over this because we did do this in class. So here I've just copied exactly what was in class that we did that Wednesday the 28th. Right, so I won't really worry about this here. But any questions here on problem 8? Okay, then let's finally do problem 9. So this says that if the supremum of A is less than the supremum of B, then you know something about elements of B. And again, we did this in class. So here I've just kind of written up what we did in class. I'm not going to go over this for the sake of time as well. Right, but this is just to say everything's in one place. Okay, so any questions here on problem 9 or just problem set number 3 in general? Okay, great. So let's move on to problem set 4. So there's a couple of these that we kind of did in class, but we didn't complete. And that's what I wanted to go over today, just to see if there's any questions on how to finish off some of these. So let's start with the very first one. All right, so this says you form the set A of x, right, from some given real number x, and you want to prove that the supremum exists, and actually that there is an integer n where the supremum is less than n plus 1. So really this problem comes down to proving that the supremum of this set is that integer n. Right, so that's what I want to go over because we kind of did this, but there were some subtleties that we left off. So first of all, we know that this set is bounded. I proved in class that the set is non-empty. So this here is just a write-up to show that the set A is a non-empty set. And again, we just did this in class. So the point is that it's a bounded set, it's a non-empty set, so that means that it has a supremum. So let's let n be the supremum here. Right, I'm going to skim over the other two because we just did those in class. Well, one of the subtleties we did not cover is that n itself has to be an integer. Right, so we know that the supremum exists, but we didn't quite show that n itself is an integer. So that's what I want to skim over here. Well, say that epsilon is given. Then if you remember back to the statements that we've been writing all along, there should exist some element in A where n0 plus epsilon is greater than the supremum. Remember, this is this whole thing that I've been stating about the whole idea of the supremum is that if I add epsilon to that number, it'll be greater than the supremum. So that's what this here says, that there's some element in AX where if I add epsilon to n0, then that will be greater than the supremum. So this here just kind of gives some reasoning behind why this is true. Now, what if I choose epsilon to be really, really small? Right, so I could choose epsilon to maybe be like 1/2. Well, now ask yourself, how many integers are there, this n minus n0, that are between 0 and 1/2? Well, there's only one, namely 0. So that means n has to equal n0, so n itself is an element of A. Right. So again, the whole idea here is that if you choose epsilon small enough, there's only one integer less than epsilon. That integer has to be 0. So that means n has to equal n0. n0 is an element of A, so n has to be an element of A. Okay, and all of this is now in the lecture notes. I did write it afterwards. So any questions on problem, I believe this is problem 1 here. Okay. All right. So let's move on here. Problem 2, I'll say that this you should be able to complete on your own. I believe that we kind of skimmed over this in lecture, but still I do want you to complete problem number 2 on your own though. So I'm just going to ignore this for the sake of time. So let's move on to problem 3. So again, we actually did this in class in detail. This was actually the whole thing of showing that between any two real numbers, there is a rational number. And again, I'm not going to worry about this. I do have the proof that's sitting here on the screen, but we're not going to worry about it because we actually did this in detail in class. Okay, any questions here on problem number 3? Okay, all right, let's keep moving here. Problem number 4. So this is one of the ones that there were some questions, but we didn't actually discuss them in detail in class. So here, this says, take a look at this set. And you want to show that the supremum exists, but more importantly, the supremum is the square root of p. Right, so I do want to skim over part B. I'm not going to worry about the other parts because we actually did those in detail in class. But I want to try to skim over a little bit behind parts A and B for this one. So for the first part, for part A, we know that the supremum exists because we have a bounded non-empty set. Right, the number 1 is in the set and of course is bounded by P. So the first half, part A, is really not very difficult. It's a bounded non-empty set, so by the completeness axiom, the supremum exists. Now what I want to do is try to show that S squared has to equal P. So let me try to do this in 2 parts. First, I want to prove that S squared is greater than or equal to P. So we'll do this by way of contradiction. So assume for the moment that S squared is actually less than P. So again, S will be our supremum. S squared is less than P. And if that's true, now I'm going to cleverly define this new quantity here, T. So T here is PS plus P divided by S plus P. Notice that this is exactly what we did in the last lesson. Right, so here intuitively, we're saying, well, if S squared is close to P, then this T squared better be even closer to P. Right, that's going to be kind of the intuition here, because remember that we have this monotone increasing sequence. So again, we're going to assume S squared is less than P, and let's define T in this way. So the first claim I want to make is that T is an element of A. Well, what that means is that T has to be positive. Well, it's positive because S and P are positive. So this ratio here is positive. And T squared is less than P. Right, so that's a little bit of algebra you have to do, but it's not too bad. So again, here I have an element T that is an element of A. Okay, so any questions so far? Okay, and I'll just leave the details here for the lecture notes. Second of all, I claim that T is greater than S. Well, it's greater than S because the whole reason of introducing this was so that we can have a monotone increasing sequence. So if I have a monotone increasing sequence, then of course T has to be greater than S. But now hopefully you see this is the contradiction, because I can't have an element from A that is greater than the least upper bound. Right, so that's the problem. I have an element of A that's greater than the least upper bound, so now I have a contradiction. Right, so that actually contradicts this here. Right, assuming that S squared was less than P. So again, I'll leave the details here, but I just wanted to kind of point out, because I know that this was a question from class. We didn't quite go over this, but here's one way in which you can do that. So just to kind of finish things off, So now we know that s squared is greater than or equal to p. And so it's not too hard to show that s squared is less than or equal to p. This was also done in class. I think that there might have been some questions about exactly what was going on. Here's maybe a slightly more rigorous proof, but this was almost word for word what was done in class. All right, so again, this here is the statement that s squared is less than or equal to p. Okay. All right, and of course, I'll leave this here on the slide so you can actually read over this and see this in more detail. So any questions here on this problem? Okay. All right. Not gonna worry about the rest of these. This whole thing here about whether Q is a complete order field, we've done this in class several times, but the point is that the square root of 3 is irrational. It's not in Q, so we already pretty much know this. So I think that should be all of the problems from problem sets 1 through 4. So again, not all of the solutions are here, but I wanted to try to at least put in one place all of the ones that we've talked about in class for those that have had questions on what was happening on this part. Is that part of the proof really correct? If you have your own proofs that are different from these, I am more than happy to see those in your problem journals. So these here are at least to say that if you're a little bit stuck, kind of confused about what's going on, then everything that we talked about in class is here in these notes all in one place. But certainly if you have your own solutions, I'm more than happy to see those and grade those. Okay. All right, so any questions about anything here before we call it a day then? Okay. All right, great. So then remember on Monday, what we're gonna do is actually start to talk about Cauchy sequences. And I do wanna try to work out some examples to kind of motivate what is the definition of a Cauchy sequence and why do we even care to write that definition in the first place. Okay, so have a good weekend then and see you on Monday.
Thank you.
You're welcome.
Thank you.
Yeah. Thanks. This was very helpful.
Okay, yeah, I'm glad to hear that. Somebody had a question here in the chat window and I can't see the chat window.
Oh. Well.
All right. I'm going to try to answer this last question here, but if I can find the window. There it is. Oh, question about the midterms. I'm going to try to have them graded by Monday. I don't know if I'll actually make it that far, but I will try to have the midterms graded by Monday. Homeworks 11 and 12 on Sakai, probably I'll have them posted by Wednesday of next week when homework set 10 will be due.
Cool.
Okay.
Thank you.
Hey, you're welcome. All right, take care then.